Myself, I am Ganga Bhavani, Assistant Professor in EC Department. Today I will discuss about oscillators. Okay, the topics include Introduction to Electronic Oscillators, Basic Working Principle of Oscillators, then Barkhausen Criteria, and finally we shall see RC type oscillators, that is RC phase shift oscillator and Wein bridge oscillator. Okay, so initially we'll just see what an oscillator is basically. Okay, oscillator is an electronic circuit which basically acts as a generator, generating output signal which oscillates with constant amplitude and constant desired frequency. That is, oscillator is basically an electronic circuit. Okay, it generates output signal, okay, which oscillates with constant amplitude and constant frequency. Okay, desired frequency. So it produces a periodic waveform on its output with only the DC supply voltage as input. So as in case of amplifiers where we give AC signal as input and we get amplified version at the output, in oscillators we are not going to give any AC input signal, just taking the DC supply as input, oscillators will produce AC output signal. So an amplifier with positive feedback itself is called as an oscillator. Then an oscillator does not require any input signal. As just I told, as oscillator does not require any AC input signal. So oscillators can be used to convert DC signal to an AC signal of desired frequency ranging from few hertz to few gigahertz. That is, you can generate AC signals using oscillators. Okay, and the frequency range of those AC signals generated by oscillators can range from few hertz to gigahertz. That is, very low as well as high frequency signals can be generated using oscillators. So that is what simple block diagram of oscillator, where DC signal is given as input and AC output, you will be getting AC signal at the output. Right. Applications of oscillators. We shall just see what are the various applications of oscillators. They are used to generate clock pulses for microprocessors and microcontrollers. Okay. So basically the oscillators are used to generate clock pulses for microprocessors and microcontrollers. They are used in laptops and smartphone processors for generating clock signals. So they are also used in laptops and smartphone processors for generating clock signals. Okay. Oscillators are also used in alarms and buzzers. They are used in radio and mobile receivers for generating local carrier frequency. Okay, so oscillators are also used in alarms and buzzers, and they are also used in radio and mobile receivers for generating local carrier frequency. Local carrier frequency is generally a high frequency signal. Okay, so to generate such high frequency signals in radio and mobile receivers also, we make use of oscillators. Then there are signal generators which is used in lab to test the circuits. So they are also used in labs to test the circuits. Okay. Used in various audio systems and video systems. Used in metal detectors, stun guns, inverters and ultrasonic. So in all such areas we are going to use oscillators. And used to operate the decorative lights also. So okay, oscillators can also be used to operate decorative lights, that is dancing lights, for example. Then you shall see the basic working principle of oscillator. Okay. So as I told, amplifier with the positive feedback is nothing but an oscillator. So here we are giving zero input signal. For oscillator we don't give any input signal, we just give zero input signal. And V naught equal to A into Vn. Here the basic amplifier gain is A. So V naught will be equal to A into Vn. And part of the output signal is given as input to the feedback network with gain beta, whose output, that is feedback network output, is given by Vf equal to beta into V naught. Okay, so if the feedback signal is added with the positive sign, okay, then you say that it is a positive feedback. So here we can see that the feedback signal is added with positive sign. So what? It is a amplifier with positive feedback is nothing but oscillator. Okay. So what will be the gain of this feedback amplifier now? Overall gain equal to A by 1 minus A beta. Since it is positive feedback, we will have the overall gain of the circuit will be given by A by 1 minus A beta. Okay. So we have got various types of oscillators, where oscillations be depending upon the value of this modulus of A beta. Okay. So if modulus of A beta is greater than 1, then you will have oscillations with increasing amplitude. As in this first case, modulus of A beta greater than 1, then the oscillations will have increasing amplitude. Okay. If modulus of A beta is less than 1, then we'll have oscillations with decreasing amplitude. But in general, what we want oscillations with fixed amplitude and fixed frequency. So if you want to have amplitude of oscillations of fixed amplitude, then we need to have modulus of A beta equal to 1. So if you see in this figure C, where you are having a sinusoidal signal with constant amplitude, this is possible only when modulus of A beta is equal to 1. So these type of oscillations are called as sustained oscillations. Okay. So to have sustained oscillations, we have a criteria called Barkhausen Criteria. If that criteria are satisfied, then we can have sustained oscillations at the output. So what are those criteria? First one is modulus of A beta should be equal to 1, as we have seen just now the 3 figures. Okay. Second one is the overall phase of A beta should be equal to 0 degrees. So the overall phase of the network should be equal to 0 degrees. A beta equal to the angle of A beta equal to 0 degrees. So from this figure we can see V naught equal to A into V in plus Vf. Okay, V naught. This is V in plus Vf because you are adding with positive feedback. So V naught equal to A into V in plus Vf. So this is equal to A into V in plus A into Vf. So V naught equal to A into Vn plus A into what is Vf? Beta into V naught, because V naught is given as input to beta network. So output will be Vf equal to beta into V naught. So in place of Vf, I am substituting beta into V naught. Then taking this V naught term to the other side, what do you get? V naught by Vn equal to A by 1 minus A beta. So for sustained oscillations, we need A beta is equal to 1. Okay. Because Vn is equal to 0, for oscillators we are giving Vn equal to 0. Vn equal to 0 implies V naught by Vn equal to A by 1 minus A beta. Vn should be equal to 0 means what does it imply? What does it imply? 1 minus A beta should be equal to 0, or simply to say A beta will be equal to 1. Okay, now A beta will be equal to 1. So 1 minus A beta equal to 0, or on the other hand A beta equal to 1. So this is called as Barkhausen criteria. Modulus of A beta should be equal to 1 as well. Angle of A beta should be equal to 0, that is 0 degrees. That is what the overall phase shift of this network should be equal to 0 degrees. This is called as Barkhausen criteria. And then we shall see classification of oscillators. Okay, there are different ways how you classify the oscillators. So first we shall see based on the waveform generated. According to the waveform generated, we have got 2 types of oscillators: sinusoidal oscillators and non-sinusoidal oscillators. Non-sinusoidal oscillators are also called as relaxation oscillators. So what are sinusoidal oscillators? The oscillators that generate sinusoidal waveform are called as sinusoidal oscillators. And the oscillators that generate waveforms other than sinusoidal, or you say non-sinusoidal signals, those are called as relaxation oscillators. So as you see here, sinusoidal oscillator, it is generating a signal, that is sinusoidal signal. Whereas relaxation oscillators or non-sinusoidal oscillators could generate square wave, triangular wave and sawtooth wave. These are just different examples of relaxation oscillators. Then based on the type of circuit used, we have got sine wave oscillators are classified as LC oscillators, RC oscillators and crystal oscillators. So in order to generate sinusoidal oscillators, we use different types of circuits. So based on the type of circuit used, we have again 3 types, that is LC oscillators, RC oscillators and crystal oscillators. What are LC oscillators? In LC oscillators again you have got 3 types: Hartley oscillator, Colpitts oscillator and Clap oscillator. And coming to RC oscillators, there are 2 types of RC oscillators: RC phase shift oscillator and Wein bridge oscillator. And the last one is crystal oscillator. Okay, in LC oscillators, we'll be using L and C components as the basic components which determine the frequency. Coming to RC oscillators, R and C are the major components that determine the frequency of oscillation. And crystal oscillators, as the name itself suggests, we are going to use a crystal to produce the sinusoidal signal. Okay. The next classification is according to frequency generated. So, according to the frequency of the signal generated, oscillators are classified into 5 types. Audio frequency oscillator, okay, whose signal ranges between 20 Hz to 20 kHz. Then radio frequency oscillator, whose frequency ranges from 20 kHz to 30 MHz. Then very high frequency oscillator, 30 MHz to 300 MHz. Ultra high frequency oscillator, 300 MHz to 3 GHz. Then the last one is microwave frequency oscillator, which generates frequencies above 3 GHz. So based on the frequency of the signal generated, you have got again 5 types. Those are audio frequency, radio frequency, very high frequency, ultra high frequency, and microwave frequency oscillators. Okay. Then according to the fundamental mechanism involved, what is the basic mechanism involved? Based on that, again you have got different types of oscillators. Negative resistance oscillators. So negative resistance oscillators consist primarily 2 terminal devices that have negative resistance in portion of its operating characteristics and a frequency selective network. For example, if you talk about negative resistance devices, examples that we can have is tunnel diode and UJT. So unijunction transistor and tunnel diode. So using these devices, okay, using these components, that is UJT and tunnel diode, we can have negative resistance oscillators. That is, after reaching certain voltage, beyond if you increase voltage also, current will be reducing. That is what called as negative resistance effect. So these using these negative terminal devices, okay, and when they are operated in negative resistance region, then if you have if you use oscillators in this region, then these are called as negative resistance oscillators. Okay. The next one is feedback oscillators. Feedback oscillators are generally simply using a feedback amplifier with positive feedback. That's using the positive feedback in the feedback amplifier to satisfy the Barkhausen criteria. So using the according to the fundamental mechanism involved, we have got 2 types, that is negative resistance oscillators and feedback oscillators. Negative resistance oscillators, what do they consist of? They consist of negative resistance devices, okay, such as UJT or tunnel diode, and also a frequency selective network. Coming to feedback oscillators mainly consist of a feedback amplifier with positive feedback and in such a way that they satisfy the Barkhausen criteria. That is, modulus of A beta should be equal to 1 and angle of A beta equal to 0 degrees. Okay, so these are the classification based on different criteria. First one was according to the type of waveform generated, then according to type of circuit used, then next we had based on the frequency generated, and final one was based on the fundamental mechanism involved. You have got 2 types. Okay, so next we shall see RC type oscillators. What are the various RC type oscillators that we have? We have got 2 types of RC oscillators, as I have told earlier, that is RC phase shift oscillator and Wein bridge oscillator. We shall see both in detail. Okay, coming to RC phase shift oscillator using a transistor, this is a circuit diagram. Okay, so we are using here voltage and feedback for a transistor phase shift oscillator. Okay, we are using voltage and feedback. Right. So we'll just try to draw the approximate model of this transistor. Right. While drawing the approximate model of this transistor, we will assume that the effect of R1, R2 and RE, effect of these resistors is negligible in measuring the frequency of oscillations. We will assume that, and we'll also assume that H0E is far less. So what we'll try to represent this circuit diagram using approximate model, approximate H parameter model. Okay. So what do we have? So basically this transistor I am trying to replace with approximate H parameter model. So I'll just have HIE and H0E on the output. Okay. HIE, HFE, IB. H0E is ignored, so I'll just have HIE and HFE. And the remaining all three RC, then CR, CR, CR. Says RC, this R1, R2, RE are ignored. Okay. Then this transistor can be written as, this transistor can be represented by just HIE, can be written as HIE. Okay. HIE. Then on the other side you'll have HFE into IB. Okay. And then from here you have RC. Okay. RC. Yeah. And while doing AC analysis, we'll set this supply to 0. So what VCC will be given to, through RC you'll have VCC given to ground. So from here RC connected to ground. Okay. Then you'll have this RC network. C, R, C, R, C, R. This is. This will be the equivalent circuit from the, if you draw the hybrid equivalent approximate model of this transistor, okay, and ignore the effects of R1, R2 and RE, then you are going to get this equivalent circuit. Okay. And finally this last capacitor, if we see, after this point RC is given to ground, and on this next side you'll have this first capacitor C, okay, R, then second capacitor C, R, and another capacitor C, followed by R3. Okay, this is R3, and next we'll have, let us assume Ri is the input impedance of the transistor. So this will be the equivalent circuit. Now what we'll do is, we'll assume that this value of R3 is such that R3 is equal to R minus Ri. R minus Ri. So that the overall resistance in this branch will become R3 minus Ri plus Ri. So minus Ri plus Ri cancel, then the overall resistance in this branch will be again equal to R itself. Okay. So the resistor R3 equal to R minus Ri is where Ri is equal to HI is the input resistance. So this choice will make the three RC sections of the phase shifting network alike and simplifies the calculations. So earlier if you see here we have CR, CR, okay, and then C, R3 in series with Ri. So if Ri is chosen to be equal to R minus Ri, then if R3 equal to R minus Ri, then R minus Ri plus Ri will give you R. So we'll have three identical RC sections. RC, RC and RC. Three identical RC sections. And we also, as I told, we assume that these biasing resistors R1, R2 and RE have no effect on the signal operation. So we'll neglect the effect of these resistors. Then by changing the current source. See, in this previous one we have the current source HFE into IB. So accordingly I had a parallel resistance RC. If I want to change this current source to voltage source, then what do I get? HFE IB into RC is the voltage source, and now this RC will come in series. See, like this. HFE IB into RC and then this resistance in series. So just replacing the current source with the voltage source, then the figure in B can be modified as this form. Okay. Now just we'll try to apply KVL to each loop. So applying KVL to each loop, loop 1, this is loop 1, this is loop 2 and this is loop 3. Applying KVL to three different loops, we'll have this because equivalent impedance of C is given by 1 by j omega C. Okay. Or it is simply minus j by omega C. So loop 1, if you apply KVL, you will get RC plus R minus j by omega C into I1 minus R into I2 equal to minus HFE IB into RC. Similarly for loop 2, minus I1 into R plus 2R minus j by omega C into I2 minus I3 into R equal to 0. And for loop 3 it is minus I2R plus 2r minus j by omega c into I3 equals, it is just applying KVL to each of the loops. You will get these three equations. Okay. Then, in the above three equations, I'll be taking r common. Okay. I'll be just taking r as common, then the modified equations will be like this. So, in each one, rc by r plus 1 minus 1 by j by omega rc. So, by taking r common in all the equations, in all the above three equations, that will result in the following three equations. So, in the next step, what I do, I'll just take rc by r equal to k and let alpha equal to 1 by omega rc. Then the three equations above will be modified like this. 1 plus k minus j alpha into I1 minus I2 equal to minus HFE into IB. Okay. So after writing these three equations, now we will try to write them in the form of a matrix. You just don't have this 0. It is equal to minus HFE into IB. So writing them in the form of a matrix, 1 plus k minus j alpha into I1 minus I2. Coefficient of I2 is minus 1, so I have written minus 1. Here we don't have an I3 term, so it is simply equal to 0. We don't have any I3 term, so it is simply equal to 0. Next, I1 coefficient is minus 1, I2 coefficient is 2 minus j alpha, I3 coefficient is minus 1. Here, we don't have any I1 term, so it is 0. Coefficient of I2 is minus 1, coefficient of I3 is 2 minus j alpha. So, these three equations writing in a matrix form will give you this one. Then, next thing, if you want to solve these equations, okay, general procedure is if you want to solve I1, the procedure is I1 equal to 1 by delta. Okay, if you want to solve I1, let me say I1 equal to 1 by delta into determinant of matrix formed by first two columns you write as it is. Okay, sorry, you want to find I1, so in first column you will replace with this term. Okay, then remaining 2 and 3 columns you will write as it is. Okay, now 2 and 3 columns will write as it is. But since I want to find out HFE into IB, that is I want to find out I3 by IB. Okay, so I want to find I3 by IB and I have IB here. Okay, I have IB here. So I'll just try to find out I3 first. So if I want to find out I3, what is the method that we are going to follow? I3 equal to 1 by delta into the matrix formed by, into determinant of the matrix formed by first two columns I'll write the same. Then third column I'll replace by this solution. Okay. So if you see here I3 equal to 1 by delta into first two columns are same. 1 plus k minus j alpha minus 1 0. Minus 1 2 minus j alpha minus 1. Okay. Third column that 0 minus 1 2 minus j alpha is replaced by minus HFE IBK 0 0. So I3 equal to 1 by delta into determinant of this, where delta is what? Determinant of the original matrix. Okay, so this is equal to 1 by delta into, now if you calculate determinant of this matrix, you are simply going to get minus HFE IB into K. So delta equal to, now what? Delta equal to, if you want to find out delta now, delta equal to what? Determinant of the original matrix. If you find delta of this original matrix, on simplification you will get delta equal to minus of 5 plus k into alpha square plus 3k plus 1 plus j into this. Then, what is I3 by IB? I3 by IB from this equation. I3 by IB equal to minus HFE into k by delta. So, minus HFE into k by delta. Delta whatever I got in the previous step, that I have substituted here. So, I3 by IB equal to this much. Now, according to the Barkhausen criteria, phase shift must be equal to 0. The loop gain phase shift, that is phase shift of I3 by IB should be equal to 0. So the phase shift, when is the phase shift going to be 0? Provided the imaginary part is 0. So from this equation, if you see the imaginary part, it is simply alpha cube minus of 6 plus 4k into alpha. So alpha cube minus of 6 plus 4k into alpha equal to 0. It is nothing but alpha cube equal to 6 plus 4k into alpha. So alpha cube equal to 6 plus 4k into alpha. Cancelling one alpha, you'll have alpha square equal to 6 plus 4k and alpha equal to root over 6 plus 4k. But what did we assume? We have assumed that alpha equal to, we have assumed that k equal to rc by r and k equal to rc by r and alpha equal to 1 by omega rc. So substituting this, okay, what do we get? Root over alpha equal to root over 6 plus 4k. So root over 6 plus 4k equal to alpha. What is alpha? 1 by omega rc. So from this, omega equal to 1 by rc root over 6 plus 4k. And omega is nothing but equal to 2 pi f. So f is equal to 1 by 2 pi rc root over 6 plus 4k. So this is the frequency of oscillations of RC phase shift oscillator. F equal to 1 by 2 pi RC root over 6 plus 4k. We'll just see what is a condition or what is the minimum value of HFE that is to have, that we need to have to get proper oscillations. So for maintaining oscillations at the above frequency, the gain should be greater than 1. So if you take that condition, you'll have minus HFE into k greater than minus of 5 plus k into 6 plus 4k plus 3k plus k plus 1. Okay. Or if you further simplification, you get HFE is greater than 4k plus 23 plus 29 by k. So HFE should always be at least equal to or greater than 4k plus 23 plus 29 by k. Okay. So if you want to find the minimum value of H of E, the procedure is, we'll derive this HFE with respect to k, that is dHFE by dk, equate it to 0. Okay. Equating dHFE by dk to 0, then that will give you the value of k. Substituting the value of k back in this equation will give you the value of HFE. So if we first differentiate this, dHFE by dk is greater than d by dk of 4k plus 23 plus 29 by k. So on further simplification, you will get k is less than 2.7. So if we substitute k equal to 2.7 in the previous equation, we will get HFE greater than 4 into 2.7 plus 23 plus 29 by 2.7. So on the whole, you will see that HFE should be greater than 44.5. So what does it mean? You need an amplifier with HFE at least equal to 44.5 or greater than 44.5. So the BJT with small signal common emitter short circuit gain, that is HFE, less than 44.5 cannot be used in this RC phase shift oscillator. Okay. And as we know, we have used 3 RC circuits, right? So if we use, so what does it indicate? Amplifier will give 180 degrees of phase shift. So in order to nullify this 180 degree phase shift, another 180 degree phase shift should be provided by the RC networks. So on the whole, we are using 3 RC circuits. So what? Each RC network will produce 60 degree phase shift. So the 3 sections together will produce 180 degree phase shift. If you are using 4 sections instead of 3, then each section should provide 45 degree phase shift. Okay. But as a result, what we are doing, we are requiring more number of components. On the other hand, if we use only 2 sections, then each RC network should produce 90 degree phase shift, but practically it is not possible. So always it is preferred to use 3 RC sections where each RC section will be providing 60 degree phase shift. Okay. So if we just quickly summarize RC phase shift oscillator, so from the basic circuit diagram, we'll assume that R1, R2, RE we'll ignore them while calculating the frequency of oscillations. Then drawing the transistor by the approximate model, okay, and then choosing R3 such that R3 equal to R minus RA, then all the 3 RC circuits will become alike. Then writing the equation in the form of a matrix, okay, then finding the solution for I3. After finding I3, just trying to write the equation I3 by IB, okay, I3 by IB, and meanwhile, while solving all this, we'll assume that RC by R equal to K and RC by R equal to K and alpha equal to 1 by omega RC. So according to Barkhausen criteria, if in order to maintain sustained oscillations, phase should be equal to 0. This is true only when imaginary part is 0. Say equating this imaginary part to 0, we have seen that omega equal to 1 by RC root over 6 plus 4k, or simply F equal to 1 by 2 pi RC root over 6 plus 4k. This is the equation of frequency of oscillations of RC phase shift oscillator. Then to derive the minimum value of HFE required, we'll take the condition modulus of I3 by IB should be greater than 1. On further simplification, we get HFE in terms, we will get an inequation in terms of HFE and K. If you want to find the minimum value of HFE, then differentiate this with respect to K, equate it to 0. That will give you a value of K. Substituting the value of K back in this equation again, you will be able to find HFE. And we have seen that a BJT with less than HFE less than 44.5 cannot be used to produce oscillations. Okay. So this is about RC phase shift oscillator. Next we shall see Wein bridge oscillator. Okay. As the name itself suggests, here you are using a bridge type of network to provide oscillations. Okay. So we are using two-stage amplifiers here. Okay. And that are designed using transistors only. Okay. So if you see here, you have two transistors. We are using two transistors, that is amplifier including two transistors, and then we are giving feedback from output to the amplifier again through a bridge type of network. That is why you are calling it as Wein bridge oscillator. Okay. If you see this bridge type network, it has got different impedances on each of its branch. Between A and B it is R1 in series with C1. Between B and C it is R2 in parallel with C2. Between C and D it is R4, and between D and A it is R3. The same thing could be modified in this form. I'm just replacing that entire amplifier circuit as a single block amplifier. Okay. Then see, output of amplifier is applied between 1 and 3 terminals. Okay, which is input to the feedback network. So 1 and 3. Okay, output is applied across 1 and 3 terminals. This is called as feedback signal. Then output of feedback network between 2 and 4 terminals is applied as input to the amplifier. Wein bridge oscillator uses a non-inverting amplifier. So Wein bridge oscillator uses a non-inverting amplifier and provides a zero phase shift during the amplifying stage. So during the amplifying stage, it is producing 0 degree phase shift. In other words, it means that the bridge network also should produce 0 degree phase shift only. So the two arms of the bridge R1C1 in series and R2C2 in parallel are the frequency sensitive arms. So we can see from this figure that these two are basically only resistors. They are not going to decide the frequency, because frequency depends basically on reactive impedances. So this branch R1C1 in series and R2C2 in parallel, these two branches are going to determine the frequency of oscillations. Okay, so if you see if we just see between the terms nodes 1 and 3, between 1 and 4 you have R1 series with C1, 1 and 4 you have R1 series with C1, between 4 and 3 you have R2 parallel with C2. Okay, and between 1 and 3 it is V0, and between 4 and 3 it is Vf. So this is the simplest circuit diagram we can analyze to derive the frequency of oscillations. So output of amplifier V0 is applied as input to feedback network between 1 and 3. So between 1 and 3, whatever you have, that is nothing but output. And output of feedback network Vf is obtained at 4 with respect to ground. So output of this feedback network is obtained at this points between 4 and the ground. This is Vf. Okay. So from this circuit diagram, I'm just writing Z1 and Z2. Z1 is equal to what? R1 plus 1 by j omega C1, and Z2 equal to R2 in parallel with 1 by j omega C2. So from this we'll see Z1 equal to R1 plus 1 by j omega C1, and Z2 equal to R2 parallel like C2. So it is R2 into 1 by j omega C2 by R2 plus 1 by j omega C2. So this is Z1 and this is Z2. Okay. Now applying KVL, we'll get I is equal to V0 by Z1 plus Z2. I equal to V0 by Z1 plus Z2. And similarly, Vf is equal to, what about Vf? I into Z2. Current flow in this branch, this impedance Z2 is I. So Vf equal to I into Z2. What is I from the previous equation? V0 by Z1 plus Z2. So Vf is equal to V0 by Z1 plus Z2 into Z2. Now usually we have the gain of the feedback network gain by beta. Beta equal to what? Vf by V0. So taking this V0 to the other side, Vf by V0 equal to Z2 by Z1 plus Z2. So beta is given by Z2 by Z1 plus Z2. Now what is Z1 we have? We have calculated Z1 and Z2 in the previous steps. So substituting those values of Z1 and Z2 in this equation beta, you will get finally beta equal to this term. And after achieving this, now we'll again rationalize the denominator. So what finally you will get beta is equal to this equation. Now in this equation, if you simplify further, you will get beta equal to this. Okay. Now, to find the frequency of oscillations, as we have seen in the previous step, RC phase shift oscillator, the imaginary terms should be 0. So in this equation, if you see what are the imaginary terms you have, equating the imaginary terms, this one is also an imaginary term. Okay. So equating the imaginary term to 0. So this is equal to 0. Then on further simplification, that will give you omega equal to root over 1 by R1 R2 C1 C2, or replacing omega by 2 pi f, omega equal to 2 pi f, you will get f equal to 1 by 2 pi root over R1 R2 C1 C2. Okay. Now, if we let R1 equal to R2 equal to R and C1 equal to C2 equal to C, then you have 1 by 2 pi root over, so this will be equal to what? 1 by 2 pi root over R1, R2 both are equal to R, then you will get R square, C1, C2 both equal to C, you will get C square. So on the whole it is 1 by 2 pi RC, or simply omega equal to 1 by RC. This is the frequency of oscillations of Wein bridge oscillator. Okay. Then we shall also derive the condition for oscillation. So to derive the condition for oscillation, substituting this value of omega equal to 1 by RC in beta. Okay. So beta, if you substitute this value of omega equal to 1 by RC in beta and equating the imaginary part to zeros, you will get beta equal to, you will have beta equal to this one. And in this, while deriving frequency of oscillations, we have assumed R1 equal to R2 equal to R and C1 equal to C2 equal to C. So substituting this in the above equation, you will get beta equal to 1 by 3. Okay. So if you want to have sustained oscillations using Wein bridge oscillator, it is required to have value of beta equal to 1 by 3. Okay. And according to Barkhausen criteria, modulus of A beta is greater than or equal to 1. So modulus of A greater than or equal to 1 by beta greater than or equal to beta value is at least equal to 1 by 3. So 1 by 3 will give you 3. So modulus of A should be greater than or equal to 3. That is gain of the basic amplifier that we are using. It should be at least equal to 3. So frequency of oscillations is 1 by 2 pi RC, and amplifier gain condition is modulus of A should be greater than or equal to 3 and beta should be greater than or equal to 1 by 3. Okay. So this is about Wein bridge oscillator. Wein bridge oscillator will just calculate the impedance caused by the reactive elements. Okay. Z2, Z1, Z2. Right. And we'll have a KVL of this circuit. Okay. V0. We'll write equations for V0 and Vf. Then finally derive beta equal to Vf by V0. That is Z2 by Z1 plus Z2. Substituting all the values of Z1 and Z2, you will have beta equal to final equation. We'll derive final equation, and after deriving, what we do is we equate the imaginary part to 0. Equating imaginary part to 0, you will get the value of F. Okay. Then substituting this value of omega back in the original equation of beta, and at the same time replacing R1 by R1, R2 equal to R and C1 equal to C2 equal to C, you will get the value of beta. After getting the value of beta, we'll substitute this in Barkhausen criteria to determine the value of A. Okay. So this gives the minimum value of A required for the transistor to produce oscillations in Wein bridge oscillator. Okay. So coming to advantages of Wein bridge oscillator, it provides better stability. Okay. Overall gain is high because of cascaded amplifier stage, and frequency can be easily adjusted by varying R or C. So advantages, coming to advantages of Wein bridge oscillator, it will provide better stability, right? And overall gain also is high because you are using two cascaded amplifiers. Then frequency can also be adjusted by varying simply the values of R and C. Coming to disadvantages, frequency is not that stable. Okay, and it also cannot be used to generate high frequency of oscillations. Both RC phase shift oscillator as well as Wein bridge oscillators, those are used to produce only low frequency signals. That is one disadvantage. Okay, so these are the references that I've been using. Jacob Milliman textbook, Integrated Electrons, written by Jacob Milliman and Christus C. Halkes. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.